Good morning, students. Yesterday, we saw some definitions of terms related to magnetism. And also, we just started discussing magnetization. So today, what we are going to do is discuss magnetization and a few terms related to that. And then we will go on describing Earth's magnetism. So let me share my screen with you. Can you see the screen now?
Yes, teacher.
So I'm starting from the topics which we covered in the last class, that we discussed a few terms which are already familiar to you, like magnets, magnetic substances, non-magnetic substances. Then also we saw a few things like what is the geometric length, what is the magnetic length of the magnet. And then we saw that the geometric length will be always bigger than the magnetic length, and their ratio for a particular magnet will be a constant. Do you remember what is that constant value? Yesterday we discussed it was 0.85. Remember that value? You may get a
Yeah,
multiple.
yeah, yeah.
Okay. Now, we also discuss what is meant by magnetic pole strength. That is the strength at the poles of a magnet. And then it is represented by the letter small m. Then what we have already learned as a magnetic moment produced by a current carrying coil, we learned the equation M is equal to NIA. Now, if it is for a bar magnet, it is small m into 2L, where small m is the magnetic pole strength and 2L is the magnetic length. That is the distance from the South Pole to North Pole. And its direction is also from South Pole to North Pole. Now we have another quantity called magnetic flux density, which is same as the magnetic field which we learned before. So the magnetic field can be defined in two ways. One as the force experienced per unit charge moving perpendicular to the magnetic field with unit velocity. And second definition for the same thing is magnetic flux density. That is the magnetic flux per unit area. Both are same, denoted by B, and having the same unit Tesla or Newton per ampere per meter. Then we learned a new quantity called magnetic intensity. Yes. Then we called a new quantity called magnetic intensity, represented by H. H is equal to B by mu, where mu is the magnetic permeability in that medium. If this is in free space or in vacuum, you can express H as equal to B by mu naught, where mu naught is the permeability in vacuum. And the permeability in vacuum, you have already learned it is 4 pi into 10 raised to minus 7. For any other medium, it will be a different quantity. So if it is inside a material, you will have to use this equation with the permeability of that particular material. And the unit of magnetic intensity is ampere per meter. And it is also called oersted. Now, a new process called magnetization. Yesterday, we saw that if we place a magnetic material like a piece of iron in the presence of a magnetic field, this is a magnet. So we know that surrounding this, there will be a magnetic field. So now if I bring a magnetic substance like iron near to it, what will happen? It will attract, and the iron piece is magnetized. That means it becomes a temporary magnet, and it is capable of now attracting another material, another piece of iron. It's only a temporary magnet because once I remove the magnetic field, what happens? It falls down, which means It is not permanently magnetized, it is temporarily magnetized. So both the process of making a substance magnetic temporarily or permanently is called magnetization. So what happens during magnetization? Before magnetization, this is the case of a magnetic material. The magnetic material contains numerous atoms. If I take this piece of iron, there are lots of atoms present inside that. And we learned that if the spins of the electrons are in opposite direction, they will cancel each other. But if there are odd number of electrons in that material, each small atom will act as a tiny magnet. But these tiny magnets, as you can see, are randomly arranged inside the piece of iron. And now when we bring this piece of iron into a place where there is magnetic field, each of these small magnets having small dipole moments, small magnetic moments will align themselves, creating a north pole and a south pole. That is how a material gets magnetized. So before we bring that material near to a magnetic field, inside that all the small atoms are randomly oriented, and therefore there is no net magnetic field. It will not act as a magnet. But once we bring that near to a bar magnet or in a magnetic field, what happens? All these atoms which are randomly oriented, or most of them, will get aligned. So one end will become north pole and the other end will become south pole, and it can act as a magnet. So this is the magnetization process. And here also they have shown, like, this is a magnet, and when it is brought near to a material, a magnetic substance, it is being magnetized by making it near to a magnet. So once it is magnetized, what happens? All these randomly aligned atoms will, randomly moving atoms will get aligned, creating a north pole and a south pole. So is the process of magnetization clear to you?
Yes, teacher. Clear.
Okay, so we have a quantity which represent the magnetization, the intensity of magnetization, or sometimes it is just called the magnetization, represented by the letter I. It is defined as the magnetic moment produced per unit volume in a magnetic substance when magnetization field is applied. So this is the intensity of magnetization, the magnetic moment produced per unit volume in a magnetic substance when magnetization field is applied. So intensity of magnetization I is a vector, and it is equal to the magnetic moment per unit volume. So magnetic moment, you know that it is also M times 2L. That is the magnetic pole strength time magnetic length. So I have substituted that value here. Instead of M, I have put it as M times 2L. And volume, you know, will be area into magnetic length. So volume, I have substituted it as A into 2L. So area into 2L. So both 2L gets cancelled. So we will get another equation for intensity of magnetization. That is I is equal to pole strength per unit cross-sectional area. So you can find the intensity of magnetization either as magnetic moment per unit volume or as the pole strength per unit cross-sectional area. So will you remember this equation? Is
Yes,
this
teacher.
clear?
Clear.
Yeah. So let us see some new quantities also related to it. uh, magnetic induction. Magnetic induction is similar to what we have seen like magnetization. So suppose here, this is a picture I have taken from your textbook because I couldn't find any similar picture. So here B naught represents the magnetic field already existing in this region. For example, if I place a magnet here, then in this region there is a magnetic field already existing due to this magnet, right? That is represented by B naught. It's in this direction. If this is the north pole, then it will be directed like this. So B naught represents the already existing magnetic field. Now we are placing a new substance, magnetic substance in this field like we did here. We are placing a new magnetic substance in this field. Now we saw that if this is north pole, this end will be south pole and this end will be the north pole, right? So for the new substance, it will act as a magnet due to magnetization. This end will become south pole and this end will become north pole. So there are new magnetic field lines which is directed from north pole to south pole outside this magnetic substance. Is that clear? This much?
Yes, teacher.
Yes, teacher.
Yes. Hasina asked me.
Clear, teacher.
Okay. So here, look here, these field lines due to the existing magnetic field is in this direction towards the right, while that due to the newly produced magnet is in opposite direction towards left. So outside of this magnetic substance, what happens? The magnetic field are in opposite direction and therefore the density of magnetic field lines reduces, which means the magnetic field strength will reduce outside because they are in opposite direction. So some field strength can cancel each other, both up and down. But inside, we know that the applied magnetic field is in this direction from right to left. And inside this magnetic substance, if the loop continues like this, it will go in the same direction inside the magnetic substance, which means there will be more dense magnetic field lines inside the substance. So inside the substance, what happens? The total magnetic field B is equal to the applied magnetic field plus the the magnetization.
Teacher,
Yes.
can I explain again the magnetic induction? I didn't
Magnetic
understand this
induction.
topic.
Magnetic induction is similar to magnetization. When magnetization happens, what happens? Substance becomes magnet, right? So
Yes.
magnetic induction is the process that explains while magnetization happens, the magnetic field lines inside the material will be more because both the existing magnetic field lines plus the newly formed magnetization field lines will add up. So the total magnetic field will be equal to the existing magnetic field plus the magnetic field due to the magnetization. So magnetic induction means the number of induction lines or magnetic field lines that pass normally through unit area around a point inside a magnetic substance. That is called magnetic induction. So that is more than what was actually existing. So more field
But
lines.
I think you said something about the magnetic density or something.
Density of the field lines. Density of the
Yeah.
field lines means more field lines per unit area is passing here, right? We saw that the magnetic field is also defined as magnetic flux per unit area. Remember, The magnetic flux means magnetic field lines per unit area. That is also B. The number of magnetic field lines per unit area is also B. So it is also represented as magnetic induction. Remember
Yes, teacher. Okay.
definition.
Understood.
Here we told that B, magnetic field B, this is same as magnetic field. This is same as magnetic flux density. That is number of field lines per unit area or magnetic flux per unit area. And B is also called magnetic induction. So there are three names for B. Magnetic induction is also B. And when you tell magnetic induction, it means the magnetic field inside this magnetic substance, which is magnetized. So for that, B will be equal to both applied field plus the new magnetization produced inside the material. That is mu naught into I. I, we know that it is the intensity of magnetization, right? And we learned that H is equal to B by mu. So B is equal to mu by H. So B naught, that is the existing magnetic field in vacuum, can be expressed as mu naught H. So mu naught becomes common here. It can be taken out. So the total expression for magnetic induction is mu naught into H plus I. See,
Teacher,
magnet, yes,
the mu naught is used when the free, it's in vacuum, right?
yeah, when it is in a vacuum.
So we're
We,
considering here it's in vacuum.
huh? Yes, I didn't
So
hear
we're
you.
considering this, I mean, we're considering this, it's going on vacuum.
Yeah, we are placing this magnetic material in vacuum or in air or in free space where another magnetic field exists. See, this is free space, air, right? So here the magnetic permeability is mu naught. Now I'm producing a magnetic field here in free space and I'm placing a magnetic substance here so that it is magnetized. So the magnetic induction inside this will be equal to mu naught times H plus I, where H is the applied magnetic intensity and I is the magnetization, intensity of magnetization. So the total magnetic field inside the magnetic substance will be this. Is it clear?
Yes.
Yes, teacher.
Okay. Now another new quantity. There are a few new terms which you will have to memorize. This is magnetic susceptibility.
Teacher,
Mag
the
susceptibility.
teacher, these terms will come only for A and B, right?
Yeah, it will come only
Then
for
okay.
A and B and maybe some problems to solve. Okay. So
Okay,
magnetic
teacher.
susceptibility is a
For
qualitative.
the problems, we will use the equation, right?
Yes, you may be all those put in boxes you will have to memorize. That's why I put them in boxes. Okay. So magnetic susceptibility is a qualitative measure of the extent to which a material may be magnetized by an applied magnetic intensity or magnetic field. Applied magnetic field, you can tell. See, uh, for example, it is a measure that represents how much we can magnetize a material. Suppose I take wood. This pencil is made of wood and I place that near to a magnet. Will it get magnetized?
No.
No. Its chances to get magnetized is very less. Or you can tell that for wood, the magnetic
0.
susceptibility is very low. Okay. So the magnetic
Okay.
susceptibility is very low. Now let me consider iron. For iron, the magnetic susceptibility will be low or high.
High.
It will be high. Okay, I'm sorry. So it will be really high. So magnetic susceptibility is a qualitative measure of the extent to which a material can be magnetized. Only if the magnetic susceptibility is very high, we can magnetize it. And you can measure it as, it is represented by this symbol, chi, chi, chi. It is read as
High?
chi. Chi.
I thought it's Kai. Oh shit.
Chi, chi. It's not X.
Sorry.
It's
Sorry.
curved X. See, the X I have put curved. Okay. So it's not X. It's chi, 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 chi. You have learned pi, phi, right? So this is chi. Chi is a symbol representing magnetic susceptibility, and chi is X with curves. Sometimes they will put one line straight and the other line curved. That's also chi. This is my handwriting. That's why both the lines are curved. Doesn't matter. So it's chi m, that is magnetic susceptibility, is equal to I. I is the intensity of magnetization. The magnetization produced in the material by the applied magnetic intensity. So more the magnetization produced per applied magnetic intensity, more will be the susceptibility. We know for wood, no magnetization is produced. So it is nearly zero. It's very low. So for certain materials, the magnetic susceptibility will be high because it can be easily magnetized. The magnetization I will be very high for the applied magnetic intensity. So that's magnetic susceptibility. Now, another quantity which is related to what you have learned before, relative magnetic permeability. We know that different medium will have different magnetic permeability. So the ratio of the permeability of the substance in a medium to the permeability in vacuum is called relative permeability of that substance. So the ratio of permeability of a magnetic substance to the permeability of vacuum. Have you learned something similar before? Relative. You must have learned relative electric permittivity in electrostatics. Epsilon R is
So
equal
we
to
used to care. No, no
epsilon
teacher.
R is equal to epsilon by epsilon naught.
No,
Relative
we didn't use them. We
is
Yes,
used
teacher,
K
we
something.
learned.
what?
So we learned K, I guess.
You just learned it as
No,
a
no.
okay. You should learn the permittivity as well. Okay, it's in your book also. I didn't teach you that part, right? Okay, so it's similar. Magnetic permeability, relative permeability is equal to mu by mu naught, where mu is the permeability of that material and mu naught is the permeability of vacuum. Now here I have derived an expression that connects the magnetic susceptibility and relative permeability. So we already know from this equation, when a material gets magnetized, the total magnetic field inside the material, which is called magnetic induction, is equal to mu naught into H plus I. And we have already learned here what I have done is I have divided throughout H. So this will become B by H is equal to mu naught into H by H, which is 1 plus I by H. Now I by H is susceptibility, chi m. So for I by H, I have substituted chi m, and we learned that H is equal to B by mu. So mu is equal to B by H. So I have substituted here mu. Mu is equal to mu naught into 1 plus chi m. Then I divided throughout this expression by mu naught. So mu by mu naught is equal to mu naught by mu naught, that is 1 plus chi m. So this becomes 1. So what remains here is 1 plus chi m. So this is relative permeability. So relative permeability is equal to 1 plus chi m. So relative permeability is always greater than the susceptibility of the material. It's related as mu r is equal to 1 plus chi m. It's better to memorize this expression. It may be helpful for you to solve numerical problems. Is this clear to you?
Yes, teacher.
Yes, teacher.
So what we have learned so far is the magnetization produced and few terms related to magnetization like intensity of magnetization I, which is equal to, what was I? I is equal to
Intensity of the magnet.
intensity of magnetization, that is either calculated as the magnetic moment per unit volume or the pole strength per unit cross-sectional area. Then we learned magnetic induction, that is the magnetic field inside a magnetized material, and it is equal to mu naught into H plus I, where H is the applied intensity and I is the magnetization produced inside the material. Then we learned magnetic susceptibility, which is I by H, and the relative permeability mu by mu naught, and they both are connected by the equation mu r is equal to 1 plus chi m. Now we will learn more about Earth's magnetism. We already learned that the whole earth acts as a magnet, right? But each point on the earth's surface can be completely specified, or the magnetic property at each point on earth's surface can be completely described using three quantities. One is called declination, represented by theta. Another one is dip or inclination, represented by delta. And the third one is horizontal component of Earth's magnetic field, H or BH. Now we will be learning these three in detail. So these quantities, which are used for completely describing the Earth's magnetic field at a point, are called the magnetic elements of Earth or the fundamental elements of Earth's magnetism. So what are the magnetic elements of Earth? What are the
Inclination,
yes,
inclination, and horizontal component
Earth?
of Earth's magnetic field.
We have already learned about one of these quantities. Do you remember which one?
Declination, right?
Yes, right. And do you remember what was declination? Do you remember what is declination?
Yes, teacher.
So let's see what is declination. Declination is the angle between the geographic meridian and magnetic meridian at a place. So what is declination? It is the angle between the geographic meridian and magnetic meridian at a place. So let us again remind us what is geometric meridian, geographic meridian and magnetic meridian. Like, is that clear to you what is geographic meridian and magnetic meridian? Do you remember?
Yes, teacher.
Yes.
Yes, teacher.
Yes.
Teacher, would you repeat?
Yeah, I will repeat. I will repeat. Suppose this is a globe, even though it's not circular. We saw that on the globe, we have a geographic north, which we call just the North Pole. And we have the geographic south, which we call the South Pole. Here you can see the North Pole and South Pole. So a line connecting the North Pole and South Pole is called the geographic axis. And the magnetic South Pole and North Pole will not coincide with the geographic North and South. They will be slightly at different point. So that the geographic South Pole will be 1750 kilometer away from geographic North Pole. So similarly, the magnetic North Pole will be 1750 kilometer away from the geographic South Pole. So they are not same points. So the line connecting the magnetic South and magnetic North is called the magnetic axis. Now, there are two lines, the geographic axis and magnetic axis. Now, when you consider any point on the surface of Earth, we can draw infinite number of planes, like containing that point and this axis and the point opposite. So if you cut at any point containing the axis, you can get a number of planes. At each point, we can get a plane which contains the geographic axis and the point at that place on the Earth's surface. So that imaginary vertical plane along the geographic North and South Pole, that is along the geographic axis at a place, is called the geographic meridian at that place. So if I cut from here, it will be like this, a plane passing through the axis, geographic axis. Now, if I cut from here, it will be another plane. If I cut from here, it will be another plane. So each point on Earth's surface will have a different geographic meridian. Is that clear? What is geographic meridian?
Yes, teacher.
And magnetic meridian similarly is the imaginary vertical plane passing through the magnetic axis. So similar to geographic meridian, we can also cut different planes from different points on the Earth's surface passing through the magnetic axis. That is called magnetic meridian. Now, the angle between these two planes or these two meridians is called the declination. So here you can see that. Can you see this figure? These two figures?
Yes, teacher.
If the compass at your place is pointing clockwise, here this is clockwise, with respect to the true north, this is the true north. Declination is positive or towards east. If the magnetic axis is like this, if this is the magnetic meridian and if it is pointing towards east from the true north, it is called positive. We tell that the declination is positive and towards east. It is pointing clockwise. So here in this region, we can see that the magnetic declination is 13 degree 9 minutes east, which means it is pointed clockwise from the true North Pole or geographic North Pole. And we call it towards east and we find it as positive. Sometimes at some places, the magnetic meridian will be directed towards west. In such cases, we call it negative. As you can see in this figure, the magnetic declination at this place is, this is New Jersey. At New Jersey, the magnetic declination is 12 degree 37 minutes west. So it is towards west, or it is in the anti-clockwise or counter-clockwise direction, and it's called negative. The declination is then called negative. Is this clear to you?
Yes, teacher.
And here I have shown the details, the magnetic declination, inclination, etc. of Dhaka. What is Wari? Is it a place in Dhaka?
Yes, teacher.
So
Yes.
in Dhaka, we already learned that the magnetic declination is 0.5 degree, right? Exactly, it is 0 degree 26 minutes. 30 minutes is 0.5 degree, but it is approximately 0.5, you can say, but it is also negative. What does that mean? It will be counterclockwise or clockwise?
Anti-clockwise.
Anti-clockwise, yes. So it is negative means it is anti-clockwise, or you say that the declination is towards the west. So when we say that the magnetic declination at Dhaka is 0.5 degree west, it means that the magnetic meridian is rotating counterclockwise or anti-clockwise with respect to the geographic north. So sometimes they may ask in question B, what do you mean